So today I want to introduce what's known as the method of brackets. So this is a heuristic set of rules. So this thing isn't rigorous yet. Actually, the first two rules have been made rigorous, uh, and the first one is a consequence, or really it's equivalent to Ramanujan's master theorem, while the second one is a multidimensional version of that. Um, but this is a set of rules for evaluating integrals on the half line. I kind of view it as an integration cheat code because it's so simple to use. What it does is it transforms some complicated integral into the solving of a linear system. So how does it work? Well, today I'm going to talk about just the one-dimensional case. Let's suppose we have an integral from 0 to infinity of some function f, which has the form sum from n equals 0 to infinity of minus 1 to the n over n factorial g of n. So g is some sequence times x to a constant times n plus another constant minus 1. So this minus 1 here is here to make what's going to follow look a little nicer. So the method of brackets tells us to treat this summation as if it converged well enough to move it outside of the integral. So in other words, let's forget about convergence issues and just move this sum outside. So obviously this looks ridiculous. This guy here diverges. But just bear with me for a moment. Let's rewrite this thing as the sum from n equals 0 to infinity of minus 1 to the n over n factorial g of n. And let's call this divergent integral alpha n plus beta, the bracket of alpha n plus beta. So maybe I should put a dot above this equal sign to know that this is a purely formal identification going on here. So here is the first rule of the method of brackets. So transform your integral into this thing, which is what we call a bracket series. And what you want to do is you want to solve for n when this bracket vanishes. So we want to find the unique solution n star such that that bracket vanishes. Well, that's easy enough. Right? This is just minus beta over alpha. We can rest assured that alpha is not 0 because we want f, our function here, to be the form of a power series. If alpha were 0, then this would just be x to some power times a constant, assuming the summation here converged. And that integral is obviously divergent. So we don't care about that case. Okay, so the first step, this is rule 1, sorry. The first step is to solve this linear system. It's just one equation, no big deal. We all learned how to do this in high school. Now, the second step is, well, let's call this integral I. The second step says that I is exactly equal to 1 over the absolute value of alpha times g of minus beta over alpha times gamma of beta over alpha. So in general, what I probably should have said here is that this is 1 over the absolute value of alpha g of n star gamma of minus n star. So the reason I change it to this other form is because when we talk about the multidimensional case, this will be a convenient form to work with. Okay, anyway, but let's work with this for now. Okay, so the claim is that any integral of this form can be evaluated like this. We solve a linear system, which is just one equation, the simplest linear system there is, and we plug into this formula, and that is the result of the integral. Okay, so we run into an interesting issue when minus beta over alpha is not a positive integer. Because all we knew about this function g was that it was a sequence. What would it mean to plug in, say, 1/2 to g? This is something that you kind of have to grapple with when you use this method. So the way one should use this is not in a rigorous fashion, but in such a way that you use it to guess the solution to an integral. And after you guess it, you need to go back and check it with some kind of rigorous method. But a lot of the times, this thing turns out to be accurate, and the extension of g to something that holds for non-integer values is usually obvious, like a factorial being generalized to a gamma function. Okay, so here's an example. Every mathematician should know several ways to evaluate the Gaussian integral. So we could do the integral from minus infinity to infinity, right? Because this function is even, and so that would be the same thing as 2 times the integral I have written here. But for simplicity, let's just keep it on the half line. So what we do is we expand this exponential, this Gaussian, in its Taylor series. We get the sum from n equals 0 to infinity of -1 to the n over n factorial. We get x to the 2n. So here is the form of the integral that we need. So our function g, or sorry, our sequence g here is just the 1 sequence, right? And it's clear how to plug in things that are not positive integers into that sequence. And moreover, what we have for alpha n plus beta -1 is 2n. So what we have is that beta is 1 and alpha is 2. And so the result of this integral should be given by our formula here. So we have, with beta equal to 1 and alpha equal to 2, we have 1/2 g of minus beta over alpha. So it doesn't matter what minus beta over alpha is. G is just the 1 sequence. This will be 1. And then times gamma of beta over alpha. That's gamma of 1/2. Gamma of 1/2 is the square root of pi. And that's exactly what the evaluation of the Gaussian integral is. So this is a really nice method. You can use it on much more complicated things. I think in another video, I will show how this thing can evaluate all the Borrmein integrals up until I believe it's the 8th iteration where a 15 is introduced in the Borrmein integral, and the integral no longer evaluates the pi over 2. And it also doesn't really give us a reason that this happens, but it indicates where it breaks down. So until next time.